Okay, now we will talk about the forward finite difference approximation. So basically, remember we can use the Taylor's expansion in order to evaluate our, or in order to actually represent our function uxt at the point x and t plus delta t. So we can see I can expand the function u in terms of the variable t, and I'm going to evaluate this at the point x and t. Okay, so we are expanding the value of this function at this point in terms of the point x and t. So you can see that this is our like f of 0 term, and then we will use the first order approximation. So we have the first partial derivative in terms of t, because we are leaving the variable x constant, so we are not dealing with x right now. And you can see that here you have t plus delta t minus t. Okay, so that's the difference. And we just have the remainder term. So the remainder term here is in the order of delta t square. Okay, and basically you can take this one of the uxt term to the left side and divide both sides by delta t. So what you get is an approximation for the time derivative. So for this partial derivative with respect to time can be approximated by the forward time step minus the current xt value, right, and dividing this by the delta t. So this is a forward finite difference approximation for this partial derivative term. So alternatively, we can take a backward time step, and this gives us the backward finite difference approximation. Similarly, so you can see that we can take a backward time step and expand this function u in terms of the point evaluated at x and t. Okay, so you can see that this time this is our t minus delta t backward time step, and we are subtracting this minus t. So this gives you the minus term here that you can see. And again, since we are just considering a first order approximation, we have the remainder terms in the order of delta t squared. So you can put this to the left and basically divide both sides by delta t. So that gives you, and also don't forget we have a minus sign this time. So this gives us the approximation for this partial derivative in terms of the backward time step. Okay, so now since we take a backward time step, this is called as the backward finite difference approximation for this partial derivative. So there is also another case, which is the central finite difference approximation. So what about if we try to combine these forward and backward time steps together? And which is of course possible. You can consider the first order Taylor expansion for ux and t plus delta t. So we are taking a forward time step and again evaluating the right hand side in terms of the point xt. So we have this plus, and you can see we have a minus sign for the backward time step. So what you get is, you can see you have the second order derivative terms. We also write them down to see that actually we will get a higher convergence rate in this case. And you can see the remainder here is in the order of delta t cubed. So basically if you subtract these two equations, again going back here, if you subtract them, what do you get, right? If you make this subtraction, you can see that you get rid of this term, right? And you have this partial derivative xt with respect to t. So we have this delta t term. So since we subtracted this, actually you have this 2 in front. And on the, let's say, left hand side, we have u xt plus delta t. And then you have minus u x t minus delta t term, right? And notice that this will cancel out. Okay, so the big O here in this case will be delta t cube here, and if you divide this both sides by 2 times delta t, so we get rid of these terms, and this is gonna be now delta t squared. So this shows us that if we use the forward and backward time steps together, and we have this 2 times delta t now, different from the previous case, so we can approximate our partial derivative using a central difference approximation, and notice that this time we have big O delta t squared. So this is, if we compare with the previous case, a better approximation than just big O delta t. So by using the forward and backward time steps together, actually we get a better accuracy, right, which is delta t squared. So this is what we have written here in equation 23. And actually you can apply the similar Taylor expansion, right? So going back to this Taylor expansion, so instead of subtracting, you can add these together. So that will give you the approximation for the second order partial derivative terms. Okay, so you can write the approximation for a second order partial derivative term using again this central approximation. Okay, central difference approximation idea. So we can again write this more formally. You can see that we this time we are taking the delta x instead of delta t, and we are fixing delta t now. So our t is just treated as a constant. We are not changing that. So we are taking the expansion of this term in terms of the x values. Okay, so we can write this. So this is again just like the forward time step, but this is a forward space step right now. And we are evaluating the right-hand side of the Taylor expansion at the point x and t. So we have this delta x squared over 2, delta x cubed over 6, etc. So you can see that the remainder is now in big O delta x to the 4. And similarly, we can take the backward space step with subtracting this minus delta x, and you write again the Taylor expansion on the right hand side evaluated at this point x and t. And basically if we add these together, so this time we are summing these two equations together, so we get this part, right? So these terms are going to the left, and on the right hand side these terms are cancelled. So what we get is this second order derivative, and again these terms are cancelling each other, so you get big O delta x to the 4. So basically our goal here is to get an approximation for the second partial derivative, right? And this is done by the central finite difference method. So this shows us that basically we can approximate first order or second order derivatives which are needed to consider or to develop these numerical methods for solving the partial differential equations. Just one example, of course, is the Black-Scholes partial differential equation.